find any of this difficult and confusing, you're in very good company. So in 1918, Einstein wrote his famous paper on gravitational waves, in which he pointed out that matter being jerked around in space-time create disturbances and gravitational waves, and derived the equation for the amplitude of the gravitational waves in terms of the time-varying quadrupole moment. But that was 1918, and about 20 years later, he and Rosen submitted a paper to Physical Review which explained that gravitational waves did not exist. They were purely a gauge phenomenon. They had no physical meaning, and they didn't exist. H.P. Robertson at Caltech rejected the paper. This was submitted to PhysRev Letters. And Einstein wrote back a nasty letter, which is still in the archives, to Robertson saying, "I submitted the paper to be published, not to be criticized." So if you ever get a bad referee's report, you know that. And after that, he never submitted another paper to PhysRev Letters. However, 1 year after the paper was rejected by Robertson, who had pointed out an error, he and Rosen sent a paper to the Journal of the Franklin Institute, a much finer journal than PhysRev Letters, saying, by the way, gravitational waves do exist. And then in 1939, he wrote a paper in Annals of Mathematics proving that the black hole solution was completely a mathematical artifact and that black holes did not exist either. So if you get confused about this, just remember Einstein was confused for 20 years too. Okay, so I have here a little summary of the LIGO detections so far. There are 5 double black holes. Some of you may have missed, there was this one that was 3 days before the neutron star, which didn't get nearly as much press as the neutron star, but it's a beautiful one, very much like the very first one. And I show the wave. That's the LIGO data up there, not a numerical relativity waveform in the time frequency map. So we now have black holes detected by LIGO ranging in mass from 7 to 36 on their way in, and of course up to 60 on the way out. And they're all, the black holes, of course, being massive and much stronger sources than the double neutron star, and so they're at roughly 10 or even 20 times the distance, because they're 10 or 20 times the amplitude. And I should point out that Virgo now actually has one detection. Virgo actually saw something for this one. It didn't see something for the double neutron star. That's how the position got good, because it should have seen something unless it was in one of the nulls of the interferometer. So Virgo finally does have an actual detection at the 4 sigma level or so. Okay, in keeping with the confusion, the detection of the operation of LIGO was a triumph for theorists, saying that gravitational waves exist, black holes exist. It was a triumph for numerical relativity, predicting the waveforms before LIGO saw them. But for some people, I have to say the double black holes were not a triumph of predictive astrophysics. So here is a paper by distinguished theoretical astrophysicists explaining that due to the large orbital period of black hole binaries, their expected merger rate is negligible, and this number is not given in Table 1. Some other idiots, Tudikov and Jungelson and Lipunov, actually did predict a significant rate, but according to our current understanding, this is a result of underestimating the effect of high mass loss and stellar winds, and so they definitely, binary black holes will not be detected by LIGO. Here's a paper by Fryer and Caligera showing over the complete range of initial masses, the final black hole mass range, which tops out at 12 solar masses, so there cannot be anything more massive than 12 solar masses that LIGO would ever see. Here's the rarity of double black holes, consequences for gravitational wave detection, barring uncertainties in physics of the common envelope evolution, which of course they understand very well. We use population synthesis and find the reduction in the merger rate of double black holes is so great by a factor of 500, their contribution to in-spiral detection rates for ground-based detectors could be relatively small, 1 in 10 compared to double neutron stars. So you remember the table, right? 5 black holes, 1 neutron star, and they're saying 1 black hole to 10 neutron stars. And so in our predicted rates for advanced LIGO, we're 2 per year at the full sensitivity. So remember, we're still a factor of 2, and therefore 8 in rate away from full sensitivity. So And here again, here's sort of a pictorial version. Here's the neutron, a different paper, but the same group. Neutron star rate, binary black hole rate, and even the black hole neutron star rate as detected by Ligo. This is not the rate per volume. This is the detection rate for Ligo. Ligo should have seen several black hole neutron stars if they found one double black hole. Okay, so clearly, I'm not showing the papers which did say that there were black holes, and some of them did have very high rates, but for 5 solar mass black holes, not 50. But clearly this part, the prediction of the rates, was not an area where theory had the same sort of triumph it did, for example, in predicting the properties of the kilonova or the properties of the black hole gravitational waveforms. Okay, so the outline, I'll start with rates and sort of how we work with rates. Then I'll talk about formation scenarios for the LIGO sources. I won't say too much about LISA. I think that's for the future talk on Friday or something. But LISA will see the same black hole binaries that LIGO sees, but several years before they come into LIGO and get arc-minute positions, so we'll know several years in advance where to look and when to look to a second in an arc-minute, which will be fabulous. And we'll see thousands of double white dwarf binaries, white dwarf neutron stars, MREs, and mergers of supermassive black holes, but I won't discuss those here. Then I'll talk about, we have formation scenarios. Is there anything we can do to actually observe the formation? Then I think I may not have time to say much about gravitational waves proper. And then I'll give an overview. What I want to spend a little more time on is an overview of the various proposals for making electromagnetic counterparts to the gravitational wave sources. And of course, everybody knows about soft gamma ray bursts and kilonovae, and we have lectures coming up later for the double neutron star. So I'll spend a bit more time on the somewhat less obvious black hole electromagnetic counterparts, where the lore was, well, 2 black holes in vacuum have no electromagnetic radiation, and then the question is, are all black holes in vacuum? So I'll talk about those. Okay, so before LIGO, there was population synthesis, and as we saw, that didn't exactly cover itself with glory. After LIGO, for the black hole, we have 5 events. On the other hand, the overall rate depends rather sensitively on what you assume about the black hole mass function. And that's still a little bit ill-determined. You can say that the only black holes that exist in the universe are those with exactly the masses and mass ratios which LIGO has already seen. If you make that assumption that the only kind of black holes are 29 plus 36 and 7 plus 14 and everything in the table, then you can calculate a rate because you know the V max for each one of those. But if you imagine that there's some kind of black hole mass distribution and mass ratio distribution, 5 events isn't really enough to constrain the mass, 2-dimensional mass and mass ratio distributions. And so a lot of this uncertainty is not really that 5 events don't determine a rate, it's the 5 events don't determine a 2-dimensional distribution. So the current best LIGO rate is that it's somewhere between 12 and 200 per cubic gigaparsec per year, with, for most reasonable distributions, or if in particular you say everything is like the 5, it's sort of nearer the upper third of this distribution than the 12 events. The double neutron star merger rate, it's 1 event, but hey, we're astrophysicists, so 300 to 4,000 per cubic gigaparsec per year is sort of the 90% range on statistics of one object. And in this one, we think that the mass distribution and mass ratio distribution is not a big problem. It's probably 1 to 1.8 plus 1 to 1.8, so it's not that one has to go from 30 to 50 or something. So it's useful in sort of thinking about models for these that we're talking of order tens to hundreds per cubic gigaparsec per year, of order 1,000 per cubic gigaparsec per year, and that's to be compared to the overall core collapse supernova rate of about 10 to the 5 per cubic gigaparsec per year. So the double neutron stars, you need about 1% of all neutron stars that get born supernovae to be in double systems that will merge in the Hubble time, and the black holes are another factor of 5 or 10 below that. Okay, so let me say just a little bit about the initial mass function. So In the old days, there was the saltpeter mass function that extended as a power law from brown dwarfs to 100 solar mass stars. It became clear a long time ago that there weren't really nearly that many brown dwarfs relative to the number of 1 solar mass stars. And so the mass function has to turn over at the low mass end, and there are various prescriptions. Chabrier and Krupa mass functions are most popular. I have here the Chabrier-Krupa is a broken power law. This one is a little smoother, cleverly defined so that there's not actually a change in slope, even though there's a change from a power law to this sort of log Gaussian. So in both of these, most of the mass is actually in the stars below, say, a half solar mass, and it's sort of concentrated in the stars around the mass of the sun, with much less mass in the brown dwarfs and in the high mass stars. And it's really rather surprising that so far as we can tell, you might wonder, can't every molecular cloud have its own mass function? Why should it be the same at low metallicity as at high? But measurements in globular clusters and lots of different star-forming regions, lots of different metallicities, would say there's surprisingly little evidence for significant variation in the mass function, and there are ideas for why density fluctuations and high Mach number turbulence produce a universal spectrum which looks something like this, and the turn-off is due to the turnover, the picking the characteristic mass scale is due to feedback.
What about different types of galaxies?
As I say, there's...
They would have the same mass function.
It might seem surprising if you didn't think that it was just a consequence of turbulence. Kolmogorov doesn't depend on galaxy type. This is high Mach number turbulence, so that's what the arguments in these papers are. But observationally, I would say if you look at different star-forming regions, you look at the numbers of heavy white dwarfs and globular clusters, which are 100th the solar metallicity, there's no evidence for anything other than that. There are a few places, like in the centers of galaxies, where there's a suspicion it might be top-heavy, but other than that, no. Okay, so here's the Chabrier IMF. So if I convert 1 solar mass of stars, I make 1 solar mass of gas into stars, I make 3 stars. So obviously, most of them must be less than 0.3 solar masses. Half of this solar mass is in stars, as I said, from 0.3 to 1. And only 2 out of 1,000 stars is in the range of 20 to 50, the sort of typical things that might be making black holes, and maybe 0.5% in the things that might be making neutron stars. So if you take these numbers... Sorry, this is in the numbers of... Yeah, the numbers of... If I turn 1 solar mass of gas into stars, I get 5 thousandths of a neutron star. Right.
But the mass is multiplied by 20 or 50 or something if I want to know the fraction of mass.
The fraction of mass that went into the initial star, the fraction of mass that went into the neutron stars is approximately this, because the neutron stars are 1.5 solar masses, so 0.007 or something. Okay, so the Milky Way today is about 60 billion solar masses, most of which is in these old stars that haven't evolved yet. The gas disk is about 1/10 of that, so it's interesting to remember that the gas disk in the Milky Way exhausts itself in only 3 billion years. The current star formation rate is about 1.5 solar masses a year. So the continued star formation in the Milky Way must be a consequence either of fountains that spray gas up and then it cools and falls back down to form another generation, but it can't be a closed box because of the G-dwarf problem, so there actually probably a significant infall of fresh hydrogen, cosmological hydrogen. Okay, so if we consider that galactic supernovae come from these 10 to 20 solar mass stars, then the formation rate of those is 1.6 solar masses a year. That's the star formation rate in the Milky Way times this 0.0053. So that's 1 neutron star born every 120 years is the prediction from the star formation rate in the Chabrier IMF. And the youngest known core collapse supernova is 110 years old. The next youngest we know about is 300. So that seems pretty consistent with a rate of 1 every 120 years. So interestingly, the number of neutron stars in the Milky Way, given that I have half the mass went into these old stars that are now the stellar disk, it's roughly almost 1 billion neutron stars in the Milky Way. So, a lot of neutron stars running around. Okay, so that was the Milky Way. How do we scale to the rest of the universe? So we have the star formation rate in the Milky Way, we have the bulge mass, we have the disk mass, and so there's several ways you might scale the Milky Way to the rest of the universe. You might scale by the current star formation rate, so that's in O and B stars. So you can compare the star formation rate in the Milky Way to the star formation rate per unit volume from H-alpha surveys, for example, that measure the ionizing flux per unit volume in the universe out to the nearest 50 megaparsecs, Rob Kennicott and company. And that, if you scale in that way, then a rate of things that form in the Milky Way, you multiply by 0.016 per cubic megaparsec, and you get the rate per unit volume in the local universe. If you scale by blue light, you look at the blue light density in the universe compared to the blue magnitude of the Milky Way, then you get something like 10 to the minus 2 rather than 0.016, so it's a little bit lower than that. So this was the rate that I invented long ago. The Milky Way mass has changed, the local blue light density has changed a little bit, and the result is still exactly the same. And this is sort of the Ligo standard, that when Ligo is doing rates, they scale, say that whatever the Milky Way rate predicted from some population synthesis, they divide by 100 per cubic megaparsec, and that's the volume rate in the universe. But another way you might scale is just imagine that, say things were an old population and just scale by stellar mass, which elliptical galaxies have negligible current star formation, but a lot of mass. And in that case, the rate per unit volume is the Milky Way rate times 0.0015, so 3 times lower than this. So you should be careful that when you're scaling from the Milky Way to something else, you better make sure you know what population your formation scenario is attached to. If it's old stars, you want to use this one. If it's middle-aged stars, you want this one. And if it's very young stars, you want to use that one. Okay, so once you have it at redshift 0, as LIGO is the highest redshift of the LIGO black holes is 0.11, and as LIGO starts improving its sensitivity, when we'll get out to cosmological redshifts, and just to remind you that sorry, was there a question? The star formation rate in the local universe increases quite dramatically, roughly 1 plus redshift cubed. As you go up in redshift, up to a peak by where it's the star formation rate per unit volume is roughly an order of magnitude larger at a redshift of 2 than it is locally. So even if you're looking only at redshift 0.3, there can be significant changes compared to redshift 0. So if you want to calculate a rate per unit volume of some event, then here are the handy formula you need. And you just need to put in this co-moving rate, which is evolving with redshift, and then integrate over the cosmological volumes to get the formation rated weight per unit volume out to larger redshifts. Okay, so now let's turn to the scenarios for the formation of these objects. So just to remind you, if I have time, Rame, I think, didn't get to doing the merger time goes as a to the 4th, so maybe I'll have time to do that. But if you take that formula as given, then you can work out that if I wanted to merge 2 neutron stars of 1.4 solar masses in 10 to the 10 years, I have to start them off with an orbital period less than roughly half a day, less than 12 hours. Otherwise, the merger time is much longer than the age of the universe, and they won't become LIGO sources. And that corresponds to a separation of about 4 solar radii. Right? So the progenitors of these would be filling the Roche lobes if they were anything other than the cores, helium cores of stripped stars. Everything else would be bigger than that. So to make these close binaries, you either have to take the 2 neutron stars formed separately far apart and have a mechanism for bringing them close together by dynamical interactions, or you have to make them by supernova explosions of very compact helium cores that didn't have too large a kick velocity to unbind them, or at least not remembering that the formation rate we want is at least 1% of the core supernova rate. We better not unbind more than 1% of them. If you do 30 solar mass plus 30 solar mass black holes merging in a Hubble time, there you can afford to have them at 43 solar radii, but that's barely enough to fit in a helium core of 30 solar masses, so they're almost the same problem. They're basically contact binaries if you try to make them out of stars, and that corresponds to an orbital period of 4 days. Okay, so in the traditional formation, we have fusion in the cores of stars makes the heavy elements in the core so that the mean molecular weight in the center of the star is different than the envelope. Then the stars swell up to very large radii, like 1,000 solar radii, and therefore if I have any of these close binaries, they can only have got there if they were once inside the other star, so it was a common envelope evolution. So that's the standard simple story. So in the field, if I don't have complicated dynamics, or I don't have triples or quadruples or sextuples doing dynamical things later, if I have a merging compact binary that started off as a binary star, it can only have got there by common envelope evolution. So all of the standard scenarios, if you look off, you start with two massive stars, say an O star and a B star. The more massive one fills its rush lobe, transfers some mass to this one, leaves one of these nice compact helium cores in a now somewhat heavier hydrogen-dominated star. This little core goes supernova. Then this more massive star begins to evolve, swells up, fill its rush lobe. Now you have this very massive object decreting onto a significantly less massive object that's dynamically unstable, as we saw in the common envelope lecture. So we get a common envelope. This thing gets buried in the compact object gets buried in the envelope of the initially less massive and now more massive star. And then basically there are two possibilities that we discussed. Either the common envelope evolution, the orbital energy succeeds in unbinding the envelope, and I'm left with the compact object in the helium core of this thing, which can then go supernova and make a double neutron star. Or if the kick velocity or mass loss is too large, it could unbind it and just make two neutron stars escaping at high speed. And we see lots of neutron stars running around the galaxy at up to 2,000 kilometers a second. So they're clearly your mostly escaped systems. There are very few in the close binaries. Or the other possibility I mentioned is the common envelope does not succeed in ejecting the envelope, and then you end up with a common envelope with a compact object in the middle of the envelope, and that's the Thorne-Zhitkov objects, where you have a star that's powered by accretion or nuclear reactions on the surface of the neutron star or black hole in the center. Okay, and if I manage to get this channel, if my kick velocity of the second supernova, or the first one too, doesn't unbind the system, then I can have a merger, and if it's a neutron star, make a short GRB, and certainly make a LIGO source. Okay, so the important point is common envelope. Right? If you want to make the particular first LIGO source, and this is roughly the same numbers as for the fifth LIGO source, it was also roughly 30 plus 30 solar masses, it's actually a little bit of a struggle in the standard model. So this is from Belchinski et al., their favorite model. They chose very low abundances to sort of try not to have too much wind so they could keep most of the mass around, because if you wanted to make a 30 solar mass helium core and you have a lot of mass loss, there's a problem. So they reduce the metallicity and reduce the mass loss. So they started off with roughly 100 solar mass and a 60 solar mass star. The 100 solar mass fills its rush lobe, transfers some mass, leaves behind the helium core and the now 85 solar mass star on the other side. This one, the 39 solar mass helium core, continues its evolution, fails as a supernova, and just basically the whole thing goes in and make a black hole with 35 solar masses. Then this 85 solar mass star begins to evolve. You got the gigantic common envelope. And now let's look at the orbital period, the separation. So they started this off as a binary with a separation of 2,500 solar radii. Okay, so this is like 10 astronomical units somewhere out at, they're orbiting out near the orbit of Pluto or somewhere. Then by this stage, it's out to 3,500 solar radii. This stage is 3,700. And here, the orbital separation is like 4,000 solar radii. So this is bigger than our known solar system. And now this common envelope takes this thing in from 4,000 solar radii to 40 solar radii. Goes in by a factor of 100. Then they get the helium, the massive helium star of 37 solar masses. This one makes a black hole, and then they have the merger. Okay, so this envelope, so they need it this big so that they can actually afford to eject the envelope and get this very small separation. And they need it big because if they had it any closer, then they wouldn't have been, then the in-spiral would have been unable to produce the final system. So you're kind of stuck with these enormous sizes and rather surprising common envelopes. So another possibility, which has been raised, was raised actually before the LIGO events were discovered, so it's not just an after-the-fact explanation, is that the reason that stars swell up is because the mean molecular weight in the core becomes different than in the envelope. And so the burning has to become shell burning, and you need to have an extended envelope because of the steep gradients. If you mix the whole star during its evolution, as I discussed in the first lecture with, say, the two stars are close to each other, therefore they're tidally locked. If they're close, they're therefore rotating rapidly. And if they're rotating rapidly, then, at least for some people, the Eddington-Sweet circulation will happen and mix the stars. And if it mixes, then the whole star it's not that the core becomes helium, it's you continue hydrogen burning until the whole star is 99% helium. And it doesn't swell up significantly. It just turns from a hydrogen main sequence star to a helium main sequence star with no giant branch in the middle. So I can start off with a system of 70 plus 60 solar masses with a 1-day orbital period, and I end up with 2 helium cores and a 1.5-day orbital period, and they're both 60 solar masses. They've had a little bit of wind loss. Then you have this collapse and make a black hole out of this one. You have a collapse and make a black hole out of that one. And basically the orbital period is hardly changing all through this stage. And these are massive enough that you would need quite a large momentum to have very much of an influence with the kick. So I don't even remember whether they put a kick into this at all, but typical ones would not have a big influence. But basically, there's no need for a common envelope because the stars don't evolve. They just turn from hydrogen into helium. The helium quickly evolves down after that through the carbon and silicon burning into iron. Then you have a core collapse, and you just make 2 close black holes if you started with a close binary. And as we saw, a large fraction of massive stars, O stars, actually are already in close binaries of this type. So if you can just avoid spiraling them in and making them all into Thorne-Jitkov objects, then this way is a very nice way of getting close binary black holes, but it crucially depends on having this very effective mixing, which is somewhat physically uncertain. Okay, so those are the standard ways of making the double black holes and similar scenario, of course, for neutron stars, except probably with larger kick velocities, of making them in the field out of just stars that are born in binaries. Now, the other method, which has been around even before the days of common envelope, well, I guess it was invented roughly the same time. People have been, since the 1970s, have been wondering about, suppose I make black holes and I make them in a dense stellar environment. In a dense stellar environment, in the very center, even if I have completely single stars, the black holes are the heaviest things. They'll sink to the center, make a tightly bound little mini cluster in the center of the larger, say, globular cluster of stars. And if you take a group of IMF and a sort of typical 10 to the 5 solar mass black holes, that's roughly 250 stars of more than 20 solar masses, and maybe 100 of those are black holes. The rest might be neutron stars or things that have escaped. So we're talking, it's not a lot of black holes we're talking. It's 10 to the 5 solar type stars, but it's like 100 black holes are what you predict coming out of the IMF. So they sink to the center by dynamical friction. And as I said, even if they're single stars, the concentration of those 100 black holes is so high that occasionally 2 of them will be close to each other when a third one comes by, and it will remove enough energy to make them into a bound binary. Once they're in the bound binary, passing stars and black holes will remove energy from it and harden the binary. More likely, we now are pretty sure that globular clusters, at least 10% of the stars are already in a binary. And when you have an encounter between a binary and a massive object, the three-body exchange typically puts the three stars roughly into equipartition, which means that the heaviest one has the lowest velocity, so it's the one that always gets left behind in the binary, and the lightest star gets ejected. So in that case, the binaries tend to be heavy. They sink in with the black holes, and the black holes just immediately exchange into binaries. So you don't even have to wait for the three-body interactions typically. Now, as the black holes, as more stars and other black holes go by, the rule is hard binaries get harder and soft binaries get softer. These are pretty hard binaries. They get closer and closer and closer. And
excuse me, what does hard mean in this case?
a hard binary is one whose binding energy per unit mass is larger than the square of the velocity dispersion in the cluster. And a soft binary is where the binding energy is less than the velocity dispersion in the cluster. So it's basically whether the binding energy is large or small compared to KT, the sort of average MV squared of stars in the cluster. And so the results you can show, that was first showed by Higgy in the 1970s, is if you have very wide binaries, then passive stars, basically passing stars, just ionize them. Whereas if you have a tight binary, a passing star typically removes some energy, so the binary gets a little bit closer, a little bit harder, more and more bound. So weakly bound things get less bound, and tightly bound things get more bound. Hard binaries get harder, and soft binaries get softer, is the phrase to remember. Okay, so as the energy is removed from these black hole binaries, their mutual orbital velocities get larger, and that means that if, say, two of these black holes in a binary encounters another black hole that comes by, the recoil velocity from the three-body interaction, which, say, exchanges one black hole for another one, is typically something like half the orbital velocity. But in order to get them close enough to merge in a Hubble time, the orbital velocities need to be of order 100 kilometers a second. Half of that is 50 kilometers a second, and 20 kilometers a second is already unbound you from the globular cluster. So in simulations of the evolution of this, most of the black hole binaries get kicked out of the cluster before they get close enough to each other to actually merge in a Hubble time. So you don't, even though, remember, we started with 100 black holes per globular cluster, 80 or 90% of those are going to get kicked out before they're in a binary hard enough to merge, so it's just like 10 or 20% that survive as binaries that are close enough to merge. And the interesting point is that the ones which do get close enough to merge, it's usually ones that were in a fairly wide binary, so they hadn't got kicked out before, which have an encounter which enormously increases the eccentricity or decreases the semi-major axis or both. And those encounters typically have a large recoil velocity because they're making a big change in the size of the orbit. And so this last encounter, the one that gets them close enough to each other to merge in a Hubble time, almost always ejects them from the cluster. So the result of that is if you want to test this scenario, you should not look to see whether black hole mergers actually happen in globular clusters, because they shouldn't be happening in globular clusters. They should be happening in things that were ejected from globular clusters 5 billion years ago and have been zipping around the galaxy at 150 or 100 kilometers a second for the last, since they were born. So they're now many, many kiloparsecs and have been lost from the cluster. The other thing you might think is, well, these encounters, they have a thermal eccentricity distribution. The mean is about 0.6. So obviously I should look for eccentric binaries, but no, as Raym explained, if you have gravitational waves in an eccentric binary, they're removing all the energy at the closest passage. So it's a drag force at pericenter, and that just reduces the apocenter until the apocenter is comparable to the pericenter, and then it becomes a circular orbit and spirals in. And so things that started off with an eccentricity of 0.6 of 30 solar mass black holes, by the time they enter the LIGO band at 10 hertz, the eccentricity is 10 to the minus 8th. They're circularized. So things that form by these mechanisms are pretty circular, but so are these by the time you see them, so it's not very diagnostic. Now, so as I said, roughly 80 or 90% get ejected early. So we'll say there are 10 binary black holes, so that's 20 black holes. That's 20% of the 100 we started with. That was fairly optimistic. Over the age of the universe, taking the space density of globular clusters, we get a merger rate of 4 per cubic gigaparsec per year. And remember, LIGO wanted 12 to 200, with sort of the reasonable guesses being in the upper half of the distribution. So this is really kind of a struggle. Now, of course, if you're a theorist, you can say, well, globular clusters, those are boring. We'll invent 10 to the 7 solar mass, ultra-compact nuclear star clusters like the Arches and put thousands of them in every galaxy, and then, well, of course, we can explain the rate. And yes, there are many papers saying that. But, we don't know about those systems. If you just do it with globular clusters we know about, this is 4 is pretty optimistic, and 1 or 2 maybe would be a little more comfortable. So there's this nice paper by Abbas and others in 2017 who did work with the globular clusters, and they worked pretty hard. They could get 5 or 10 maybe. Rodriguez et al. Had some of the versions with the, let's put piles of 10 to the 7 solar mass dense clusters in every galaxy that we haven't seen yet, and then we can explain the LIGO rate. Now, yeah?
So in the evolution scenarios that you showed for the field binaries,
Mm-hmm.
it seemed like the two models that you showed, they had predicted very different merger times from like 0 age. So is it possible to constrain the merger times from LIGO observations at all?
I mean, how long? Well, so for the black hole systems so far, no, because we don't actually have an identification of a host galaxy for any of them. For the neutron star, it's quite interesting, actually. I would say that the galaxy that the first LIGO event was found in was not one which you would have rationally predicted would host the first neutron star. It should only be hosting roughly 1% of the double neutron star merger rate. So it's a little surprising that the first one you found was in an old dead galaxy with no star formation in the past 5 billion years. But for the black holes, we don't have any analogous thing. We don't know whether these are in massive star-forming galaxies or old dead ones. We just don't know.
Actually, on the list of galaxies to look at, this was the 3rd or 5th, depending on how you made the list. So,
No,
so I'm
no,
not
no.
sure about your statement.
No,
This is-
the statement, I stand by the statement absolutely. It was on the list because they were going down the list by luminosity.
which is the right thing to do.
Well, we can discuss that later. These scenarios is the loop, because that system has not made any stars at that point. For only the limit on the star formation in that point in the last 5 billion years is less than 1% of the mass of the galaxy. So all of the systems in that galaxy must have had in-spiral times of 5 to 10 billion years. Whereas most of the rate is actually in things with shorter in-spiral times. So it's a puzzle, I would say. Yeah. I mean, at the time that they put it on the list, they didn't know whether it was star forming or not. They just put it on the list with luminosity. But if you scale with star formation rate, so I have lots of slides on that if you're interested. Okay, so the other way is, well, triple systems are great, globular clusters are great, but we can have triple systems in the field. As I told you in the first lecture, massive stars are typically in 3 and 4 body systems, so we don't even need the globular cluster. Each massive star just comes with 3, 4, or 5 companions. So it can sort of do things kind of like happen in the globular cluster, and you just have to be careful that you don't strip off the 1 or 2 stars that are available to harden the inner binary. If you start off with fairly close, so they're fairly tightly bound near equal mass triples, then, with the significant inclinations, then you can push the inner binary to very high eccentricity and get a rapid merger. You don't want to do it too early because then you merge the stars while they're still on the main sequence. But there's a nice paper by Silsby and Tremaine that tried to go through everything fairly carefully. And they argued that they could get maybe 6 per cubic gigaparsec per year using the triple and quadruple fraction, which I showed you in the first lecture for the field binaries. But very importantly, the black holes have to have no kick when they form. And the problem is that if you're relying on a third companion when the first black hole forms, if you have a significant kick, you basically unbind the triple system, and then it doesn't have any cosi anymore. So if you give natal kicks of 40 kilometers a second, and roughly somewhat more than half of the galactic black hole binaries that we know about with black hole plus a main sequence star, so the X-ray transients have velocities going up to 200 kilometers a second. But there are some that look like they could be lower, and there's certainly observational selection effects against finding the ones with low kicks because they're in the galactic plane with a huge obscuration. So I think this is possible, but in any event, this is sort of like the globular cluster rate. It's the pretty low end of the LIGO rate. So if LIGO continues finding these things at a high rate and the rate converges on 100 per cubic gigaparsec, neither this nor the globular clusters are, they certainly probably happen, but there may be less than 5 or 10% of the overall rate. So those were the sort of most common scenarios. I'll discuss some other ones later when we talk about the electromagnetic counterparts of making things, forming stars in the accretion disks around active galactic nuclei and capturing them, and those also are typically rather small rates, but they're especially interesting for electromagnetic. So let's ask about, could we actually see some of these formation scenarios actually just happening in the sky? So black hole formation from the LIGO rate is roughly 1 per year at 150 megaparsecs whole sky. So we want to be looking for a transient event, monitoring the whole sky out to 150 megaparsec, and we'll see one common envelope evolution, for example, where a black hole or neutron star spirals into another star. And that's the rate at which we expect to, in the common envelope scenario, for example. The problem, I would say, with looking for long, slow, decades-long things, aside from all the red supergiants and Miras and things that have long, slow variations, is that basically it doesn't really matter if you put in a 1 solar mass neutron star or a 1 solar mass main sequence star, you get the same common envelope evolution. The only difference would be if the neutron star was really accreting at 100 times Eddington and producing some spectacular radiation pressure-driven jet. You might be a common envelope with a relativistic jet coming out of that you might notice. In the dynamical formation model in globular clusters, there are lots of heavy, but you're postulating that there are hundreds of black holes of 20, 30 solar masses running around in the globular clusters, and they can damage main sequence stars and maybe most interestingly white dwarfs and make sort of little mini TDEs. SS433, the famous object which maybe young people don't know about, what was the most exciting relativistic astrophysics object when I was young, is this object with precessing jets, velocity of 0.26 c, H alpha jets with a Mach number of 10 to the 4, precessing around, corkscrew radio jets, eclipsing X-rays, the whole shebang. And we still, I think, don't absolutely know whether it's a neutron star or a black hole, but it clearly is something which is, there's an incredibly massive star accreting onto a very compact object with relativistic stuff coming out with unbelievable detail that almost certainly is going to evolve into something that will be either a double neutron star or neutron star black hole, or black hole, black hole. So one might look for extragalactic versions of SS433, since those are clearly things that are probably going to evolve into these. So, as I say, it's a little bit daunting to imagine monitoring of the whole sky for sort of things that might have other explanations out to 140 megaparsecs. So the other way is to look in the Milky Way. So I think one thing which I think is particularly interesting for the people who want lots of black holes in the globular clusters, the black hole binaries are great, but the thing that's really spectacular is that in the lower density clusters, where the black holes haven't all segregated to the middle, there should be lots of main sequence stars orbiting 30 solar mass black holes in fairly tight orbits, and those will have orbital velocities of 100 kilometers a second. And so you take spectra of the cluster members, determined from Gaia, for example, or something by proper motion, so you know they're members. And if you see something with an orbital velocity of 100 kilometers a second that's varying on time scales of days or weeks, but as a cluster member, then you're pretty damn sure that it's orbiting a 30 solar mass black hole, and there should be dozens of these things in every globular cluster. So if you have something like set PFS with 5,000 fibers, you just put them one on each star and you wait till you find one of these. And if you don't find them, then there probably aren't all these black holes that were postulated. There's still the issue that most common envelopes, probably, or a significant fraction of them, probably fail. So there really ought to be Thorne-Zhitkov objects unless everything accretes and they have very short lifetimes. So looking for P-process elements or the neutron star versions, I think, continues to be quite interesting. So far, all the Thorne-Zhitkov objects that have been discovered have turned out to either be quasars or to have other possible explanations. So there's still no, at least that I know of, absolutely convincing Thorne-Chitkov object. In the hierarchical triple systems, one could look for the black hole plus the main sequence star. You can look for them just from radio velocity monitoring, basically like this. But so for example, with Gaia, you look in ultraluminous X-ray binaries to see if the central source is not actually one black hole, but two black holes orbiting each other, accreting from a third one. So those would be progenitors for the sort of the merger scenarios when the triples or quadruples. Rotational mixing, I think there's little bits of evidence that suggest it might be happening of anomalous binaries with anomalous ages in the LMC and funny nitrogen abundances. But it would be really not, I would say the theoretical arguments are going both ways and the observational evidence is going both ways. So I think this is still attractive, but by no means proven that this happens. And then there's also the question of, although Ligo now does have a couple of 7 and 12 solar mass black holes that overlap with the masses that we see in X-ray transients, we still in the X-ray transients haven't found any 30 solar mass black holes, which LIGO is finding many of. And so there's a question, are there selection effects? For example, the more massive black holes might have lower kick velocities, and most of the X-ray transients that have been optically monitored to determine the masses of the black hole are the ones at high latitude with little reddening, so in the optical it's easy to study them, and therefore they must have had high kick velocities. But if the more massive black holes get lower kicks, then they'll be in the galactic plane where there's 30 magnitudes of extinction, so nobody's bothered to measure the masses. So there might be a strong bias, but now we have very nice infrared spectrographs, so you can go after quiescent X-ray sources in the plane and try to get radio velocities in the infrared, and Peter Jonker has a big team that's starting to do that. And finally, there are sort of beautiful ideas of using VLBI microlensing measurements. So you monitor compact objects in the radio, look for things that might be microlensing events, then go after them with VLBI to see if they're actually your two images, and monitoring a few thousand, which we're already essentially doing, we could actually get a mass function for single black holes, and if the double fraction was large, also the doubles even more beautifully, just from microlensing experiments in an unbiased way that doesn't depend on there being in binaries and so on. So we could actually learn about the single mass function. Okay, I think maybe in the interest of time, if anybody's really interested in the gravitational waves and gravitational wave detection, we can do this at the end or some other time, but maybe I'll go on to the electromagnetic counterpart. So let me now start going a little bit through ideas of electromagnetic counterparts. So I'll start off with this version, which I think is the simplest and stupidest way to get an electromagnetic counterpart to a binary black hole. And it absolutely happens. I think 5% of all emerging black holes absolutely must have electromagnetic counterparts. They'll be very faint and hard to find electromagnetic counterparts, but they absolutely will be. And the reason is, as I told you, the typical massive star is not in a binary system. It's in a triple or quadruple. And so if, in particular, in the homogeneous evolution model where the inner binary never expands very much, I start with a close inner binary. It evolves to make two helium cores. The two helium cores make two black holes, for example. And this third star is still left orbiting, unless you have a very large kick and unbind it. But you'll have this third star orbiting the merged one. And this third star typically has a mass drawn from the Krupa IMF relative to these. The two close binaries tend to be correlated in mass, but the wider separations are uncorrelated. So this is just some 1, 2, 3, 4, 5 solar mass star out here orbiting this binary. So after a few 100 million or a billion years, this star will evolve. It's now it's not in a tight binary, so it's not tidally locked and not rotationally mixed because it's in a wide binary. So that star will then fill its Roche lobe and begin accreting onto the binary system. Now, as it accretes onto the binary system, the circumbinary disk now feels a gas torque as well as gravitational waves, so it's driven into merger. So that enhances the rate of merger in these systems. And the only question, the calculation you have to do is what is the probability that these two objects merge while this accretion is still happening? And it could be that they're formed close enough that the accretion happens, the accretion is all over, and then they still haven't merged. Okay, but because the accretion exerts a torque that drives them closer together, it actually increases the probability. And so the calculations that Lynching Wen and I did were that a few percent of the binaries, the accretion would still be happening at the moment of merger. So if that happens, you have a pair of black holes that have a circumbinary disk. And there are lots of simulations by Andrew McFadden and others. We started off this idea with the supermassive black holes and galaxies, but it's a scale-free scenario in this case. You just reduce the mass by a factor of 10 to the 7. You have a circumbinary disk. Some material leaves in little streams and makes mini disks around each of the black holes. And so you can have emission both from the two black holes and from the circumbinary disk. This would be probably super Eddington accretion rate. So there's an electromagnetic source, but it's basically probably an ultraluminous X-ray binary. This is maybe 10 or 100 times Eddington at most. And it's roughly steady. There's nothing very special that happens at merger, right? You have an accretion disk around a close binary pair, and then the two black holes merge, and you have an accretion disk around a merged black hole. But except for the a little change in the inner edge, not very much has happened to the accretion disk. So there clearly is an electromagnetic counterpart, but it's not a spectacular transient, and it's not spectacularly luminous. But I think this inevitably happens, right? It doesn't require any special arguments. It's just things we know about stars. So there are lots of other proposals for getting circumbinary disks around black holes. For example, you could, if you just had a binary that had a common envelope evolution, you might have lost mass from L2 and left a cold binary disk. That disk might have become neutral during all the period these two black holes were gradually spiraling together. So that disk will be cold and invisible, but then when the two black holes merge, there will be some mass loss and recoil that will produce eccentric oscillations in the disk. And Demink and King, for example, proposed that that could suddenly heat up the disk and make it start accreting and shine. And this basically is sort of a version of ideas that Elena and I and Milos Milosavljevic had in previous years in the supermassive black hole binary. The black hole merger recoils and kicks will excite the circumbinary disk. So that's certainly one way. Another way is that the binary black holes were actually formed in the thin outer self-gravitating part of the disk of an AGN. So these two binary black holes are actually orbiting inside the accretion disk around a 10 to the 8 solar mass black hole. So they have lots of gas around them, and the gas is being funneled through, and that gas drag can shrink the orbit, and there's clearly gas. So it's it's another way of getting this system, but instead of putting a third star that's Roche-Lobe filling, you just put it in a giant accretion disk around a big black hole. And so there are papers by Stone and Bartos and others. On the other hand, this is binary stars in AGNs, which are 1% of galaxies 1% of the time, and so it's hard to get a very high merger rate, but it certainly could produce some gas rich. On the other hand, it's not clear to me, again, that it probably looks, I think, like an ultraluminous X-ray binary, so it's not an obvious spectacular transient. Yeah. So there are two possibilities. So one is if you form it in the outer self-gravitating part of the disk, it's actually gravitationally unstable. So one of the questions has been what happens in the Tumri-Q unstable regions of the outer parts of accretion disks. They probably form stars. And that may be where the massive stars in the disks in the center of our galaxy formed, for example, is they just formed out of the gas in the disk. And if they formed a binary, then the disk continues interacting with them. The other possibility, which is a bit harder to arrange, is that if you have stars that are formed in some other way on inclined orbits, as they pass through the disk, they can exert a wake, which sort of gradually tilts their orbits and can get them into the plane. But that requires a fairly massive disk and a little more cleverness, I think. But so I think making them in the disk is a bit better, but there certainly are papers arguing that you could torque them into the disk even if they weren't initially in it. But again, the rates are not so high. The last idea is the idea of the sort of zombie disk. So the idea is that rather than a circumbinary disk, the idea is that you might have had some inner accretion disk like this one, which again, over the billion years of the evolution, became neutral, therefore no longer in AMRI, so it has no viscosity. It's just this cold neutral disk orbiting. And then as the two black holes get close enough to each other, the tides, so rather than a circumbinary disk, this is now intrabinary. So as one black hole gets closer, the tides perturb the orbit of this neutral disk, shock the neutral disk, it becomes ionized, and suddenly the MRI turns on. And so this is a way of actually getting a flash just before merger. I think the others are probably just sort of continuous X-ray binaries. This would actually be a flash. I think the issue there is how much mass can you actually keep orbiting at 5 gravitational radii around the black hole. When it was ionized, it probably, I would have thought most of it would have accreted. But if you could keep a significant mass, that certainly is a nice way of getting a flash. And then finally, there's always somebody who says, oh, well, the black holes actually have firewalls and it's all quantum gravity and they'll produce spectacular electromagnetic signatures, right? So, maybe. Okay. There's one other interesting idea, this is posed by Erez and Peretz, of precursors to black hole mergers, not transients that happen just seconds before or minutes afterwards, but 100 years beforehand. And so the idea here is that if let's say we make one neutron star, now in a helium core orbiting it. Now the second helium core has a kick velocity when it's born, and most of the time the kick velocity unbinds the system or changes the eccentricity, but sometimes say the systems are in a circular orbit, the kick velocity will be equal and opposite to the orbital velocity. So it will give the final neutron star zero angular momentum with respect to the other one. So the other one will fall nearly radially into the second neutron star. And those very highly eccentric systems can have very short merger times because the pericenter would just be a few gravitational radii or a few neutron star radii. And so that doesn't happen very often, but you can work out if you have a distribution of kick velocities and a distribution of orbits, what fraction of the time you have this almost perfect cancellation, so you end up with a radial orbit. And you find that there's a tail of, depending on the initial velocities and kick velocities, of maybe a few tenths of a % of systems that will have merger times as short as 1 or 100 years. So then the neutron star that formed in the supernova explosion with the kick, which gave it that eccentric orbit, would be the thing which led to this very short merger time. So there would be a supernova, which gave the kick, which canceled the orbital angular momentum and drove the merger to happen, 1 to 100 years before the merger. So once LIGO is getting thousands of merging neutron stars every year, we get good positions for all of them from all the thousands of transients electromagnetic transients we'll observe from those, and you can now go back and look in the archival plates or previous decades of PTF and ZTF and pan stars and so on to see if there was a supernova at that position. So that's the prediction. Okay, so before I go to the blackboard, I just thought I'd show you a nice Christmas card I got 2 days ago. So my former postdoc Kumiko Patera every year sends these amazing Christmas cards, and I thought this one was quite nice. So this says, in 2017, 2 neutron stars hugged. It was a revolution for astronomy, ensuring that 28 years will be novel, exciting, and bright. And I thought this was particularly nice because you see the 2 neutron stars, which I think are actually her older son and her new baby. But there's the disk of tidal material. Then there's the collisional ejecta with both the red and the blue components in them and everything. So this was really quite a nice Christmas card, I thought. So, so as you hear over the rest of today and tomorrow and Friday, you'll learn about the red and the blue components and the collisional ejecta and the tidal debris and so on, and the 2 neutron stars. So, okay. So if I have time at the blackboard, I wanted to try to work through as much of this. I basically had 3 things I wanted to work for. So one was sort of a very quick order of magnitude estimate for the how much energy one could get for the accretion and the nuclear decays and the double neutron star ejecta. Then one electromagnetic transient idea, which I didn't discuss, is the idea that perhaps I have a very massive star with a very rapidly rotating core. As the rapidly rotating core begins to collapse, it fragments and makes two black holes out of the rotating core by gravitational instability. Those two black holes are now orbiting in the dense gas core of the collapsing star. Their drag forces will be large. The two black holes will be driven together. They're forced to merge. And lo and behold, you have a whole star outside falling in. So, of course, there's going to be an electromagnetic transient. Of course, there's also optical depth of 10 to the 20 to the gamma rays. And so how you get the gamma rays out in 3 seconds is a problem, possibly. But anyway, that didn't disturb either of these authors. And then finally, the idea of suppose that we have neutron star black holes, which we haven't found yet. There's the interesting possibility that many neutron stars have strong magnetic fields, and so the magnetic field from the neutron star, as the black hole spirals close to it, begins to intercept the horizon of the black hole. So I can extract energy from both the neutron star and the black hole through the shared magnetosphere, and we can work out how much power we might get out of that. Okay, so if we can raise the board. Okay, so the first useful number is 1 solar mass c squared, 2 10 to the 33 grams, 10 to the 21 is 2 by 10 to the 54 ergs. Okay, useful thing to remember. So if I have two neutron stars, which are orbiting each other, if the masses are not quite equal and they're not too compact, then as they begin to get close to each other, they'll tidally distort each other, and the material on the far side of the tidal bulges can become unbound and be stripped off in the tidal tail. And simulations for unequal mass neutron stars, even including relativity, indicate that the mass loss in the tidal tail can be roughly 10 to the minus 2 solar masses, maybe 10 to the minus 3 is more typical in full GR with not too extreme mass ratios. And then as the two black holes actually first touch each other and collide with each other, there will be a shock in the collision and hot material will be sprayed out. And the ejected material, again, before LIGO saw something, the estimates were maybe 10 to the minus 3 to 10 to the minus 2. Now 500 seems like a great idea because that's consistent with what we saw, but let's just call that 10 to the minus 2 solar masses to order of magnitude. Okay, so what could we do with this stuff? This stuff is ejected at pretty high velocity, maybe escapes. This stuff is there's just tidal streamers, so it's probably not really escaping fully from the whole system. So you might imagine that this stuff, these streamers will eventually intersect and it will look something like a tidal disruption event. I can make an accretion disk out of this. Maybe some of this falls back, but some fraction of this material I might imagine accreting back onto the black hole. So the energy that I could get from accretion of some of this ejecta, if it's the usual accretion disk with 10% efficiency, it'll be 10% of 10 to the minus 2 solar masses c squared, so that's 10 to the minus 3 of this number. So delta m ejection c squared times the 10% efficiency might be about 2 by 10 to the 51 ergs. And that's a nice healthy gamma ray burst. So Udi will tell you about how to make nice healthy gamma ray bursts out of this kind of stuff. Now the other possibility is particularly this stuff, but also this, or a neutron star material, so it's very neutron rich. So as it begins to escape, there are lots of neutron captures. I make unstable R process nuclei, and as those continue flying out, those R process nuclei will begin to undergo radioactive decays. They're unstable elements, and so they'll put some heat into the stuff. So how much heat luminosity can I get out? So the nuclear, well, I should say nuclear energy input. Let's say we put 10% of the mass, so 10% of the ejected material or even the tidal material in neutron-rich elements. And when the neutron-rich elements decay, they're typically neutron-rich by having maybe 10 more neutrons than would be consistent with the usual valley of stability. And the binding energy of those extra neutrons is typically a few MeV, 1 or 2 MeV per neutron. So if we have 10 extra neutrons, each with 10 MeV, each with a couple of MeV, then we're talking about 20 MeV per 10 extra neutrons added at 2 MeV per neutron. And the typical atomic numbers are 100 or 200. So the energy per baryon, let's just to make it easy, let's put in 200 baryons. So this is, again, 10%. So we're talking 0.1 MeV per baryon. Now, then we have to ask about what are the decay times of this elements, on what time scale. And the way nuclear physics to me is very complicated. There's a Fermi barrier. The Fermi barrier can be any value. The decay time is exponential in that. So if I have random decay barriers, I get equal numbers of nuclei with every log decay time. Right? If I set the barrier at random heights, then I have equal numbers of decay times of 10 to the minus 6 seconds, is 10 to the minus 5, is 10 to the minus 4, is 10 to the minus 3, 100,000, and so on. So decay times crudely equal number every log t a half, so sort of a uniform distribution in log t a half. It's actually, if you look at real distributions, it's slightly tilted. It's not quite t to the minus 1, but t to the minus 1.2 or 1.3. So if we do this, say, logarithmically distributed in decay times from 10 to the minus 3 seconds to 10 to the 6 years, and we know nuclei over that whole range, that's a factor of 10 to the 9, which is e to the 20, so that's 20 in the log, a factor of 20 in the log. And so, as you'll see in the subsequent lectures, we're sort of interested in how much is the heat being put in over days. So if we consider, say, 1 to 3 days, that's 1 E-folding out of the 20 E-foldings, so that's 1/20th of the elements will be significant heating on the sort of 1 to 3 day time scale. So roughly 1/20th of the decay products will be heating with T a half in the 1 to 3 days. So if we put this all together, the total energy that we're going to get out, okay, we have 0.1 MeV per nucleon. Okay, that was here. 10 neutrons at 2 MeV per neutron over 200 baryons in the nucleus, so 0.1 MeV per nucleon, times 1/20th, that's the ones with t a halves of days out of the whole 10 to the minus 3 seconds to a million years, times delta MC squared. And we might put it aside that maybe not all of this went in, maybe there's some fraction f, I think it suggested 10% over there. So 0.1 MeV per nucleon is in c squared units, 10 to the minus 4 c squared. Nucleon is 1 GeV, so 0.1 MeV is 10 to the minus.
You don't want that last C squared.
Oh, so sorry, yeah, sorry, just delta M, right? Thanks. Yeah. So this is something like 5 by 10 to the minus 6 times F delta M C squared. So this is something like 10 to the 47 F ergs. Okay, so that's roughly what we expect. I think the Metzger et al. 2010 did this much better than I did and got 310 to the 36 to 310 to the 46. Okay, so this is quite small compared to the energy you can get from the accretion. So if you accrete and you make a gamma ray burst, you can get something much brighter than this. But this stuff sort of happens and is quasi-isotropic. And as you'll hear in subsequent lectures by Udi and Zvi and then Dan, we saw lots of phenomenology associated with this. Okay, so Mr. Chairman, do I have time for one more? Yeah. Okay. So let me next talk about the black hole electromagnetic counterpart. So this idea of black hole electromagnetic counterpart to a gravitational wave source, and a lot of this work was motivated by the first black hole, 1509-14. Fermi saw a 3 sigma significant event some number of seconds after the LIGO merger. They also saw something 5 minutes before and 10 minutes after and 20 minutes after. So, you know, finding some, so they calculated the probability that in a 30-second window there would be an interesting event. But you know, you might wonder why 30 seconds if the diffusion time of the gamma rays out of the star is an hour, maybe the window is an hour, and then they had 5 events, right?
30 seconds isn't that crazy.
Yes.
This is why they chose 30 seconds.
You said it. Okay, you're on record. You said it, not me. But I sort of agree, yes. And I think the reasons why you could have chosen a number other than 30 seconds. But anyway. So this possibility got a great many people excited. So as I mentioned, Avi Loeb proposed that the way to do this was to have a star. I have a rapidly rotating core. This core begins to collapse. This rapidly rotating core fissions into 2 compact objects, makes 2 black holes. The black holes are now orbiting in the gas in the center of the star, very high density gas. And so they'll be brought together. And once this happens, of course, well, you know, there's shock waves and it'll make a gamma ray burst, obviously, right? So,
Excuse me?
yeah.
You said fissions and makes 2 black holes. What do you mean by that?
So the old-fashioned way of making binary stars is to have a rapidly rotating disk, which has a lot of angular momentum, and then you try to collapse it. So the disk, if it's sufficiently massive, typically becomes bar unstable. So it makes a rotating bar, and then you hope that you can sort of pinch off the 2 ends of the bar and make 2 orbiting bodies. That's fission. So you're splitting, you know, it's like the cells in the body, taking a rotating bar and just pinching it off and making 2 bodies. So it, in in-body simulations, I mean in sort of hydro simulations, it is possible with sufficiently rapid cooling that actually is observed. It's kind of tricky to get it to work, but it has been seen in simulations. You can get the fission to work. So one interesting question, so this has been looked at by Jane Dye and McKinney and Miller, and also more recently by Fedro and others who did full 3-body, full general relativistic hydro calculations of the evolution of this inside a star and came up with the obvious answer, I think, in the end. You could ask the following question. Suppose these 2 black holes formed out of fission in the nucleus. So the gas density in the nucleus around it has a mass that's sort of a significant fraction of the mass of the 2 black holes that it's orbiting in. And you could then ask, is this gas drag so extreme that it drives the 2 black holes together faster than the gravitational wave time scale, and therefore the waveform that you saw would not fit the predictions of relativity, and therefore you could rule out this scenario. Okay, so let's see if that can happen. So if I have the 2 black holes that are orbiting with a velocity v and a medium with a density rho, then the drag force, so as the black holes are moving, there will be a wake behind. The usual Bondi-Hoyle, the gravitational attraction of the wake, exerts a drag, and the drag force is roughly 4 pi rho times the area of the focused flow, so gm over v squared is sort of the incoming radius where the flow is significantly deflected. So gm over v squared squared will be the the cross-sectional area. You can argue about whether you want the 4 there or not. And then, so that's the area. So the mass flux in is density times area times velocity, and the momentum flux in, which is the drag, is that times v squared. So that's the order of magnitude of the drag force you expect, and for the same reasons that Ray mentioned, you can put in a logarithm when you integrate over the whole length of the tail of the Bondi-Hoyle. And the drag power, of course, will be the velocity times the drag force, so the drag power would just have a v cubed rather than a v squared for the drag force. So now we can calculate the drag in spiral time. So that's going to be the time it takes for this drag force to remove the momentum. And the momentum of the two orbiting bodies is mv. So over 4 pi rho so if I wipe out the v's, I get an m. I get a 4 pi rho gm over v squared v. Now, the orbital velocity of these two black holes around each other, if their separation from each other is r, then gm over v, sorry, this is squared, gm over v squared is basically just of order r, the separation of the two black holes. So this quantity basically looks like mr over m gas. So if I had rho r cubed instead of rho r squared, that would just be the mass in the gas. So I put an r up here and then taken an r cubed down here as rho r cubed times v. Okay, so this is basically the mass in the black holes divided by the mass of gas in the volume comparable to their orbital size times r over v, and that's just 1 over 2 pi of the orbital time. Okay, so you see the obvious thing that if the mass in the gas is, some 10% at least of the mass in the black holes, that they're going to inspiral in roughly one orbit. And therefore, that would noticeably be different than the predictions of general relativity. So if you do a very fancy three-dimensional general relativistic hydro simulation, that's what you find. So they argue that, well, you can rule out, because the natural thing is that if this is fission, that the mass of gas that's left over is comparable to the mass that was in it, and therefore generically they'll inspiral a little too fast to be consistent with relativity. So that's the summary of 4 very long papers. And shall I stop, or shall I do a couple of magnetospheres? One more. Okay. If anybody has questions that are more pressing, they can just use an eraser here. Yep. If anybody, so Adam and Raim will appreciate this, but I worked out last night how many scribes are employed in Israel making mezuzah scrolls. So we can do that too, if you're interested. Fermi problems are always fun. If anybody knows the answer, let me know, but I got 1,000. So. Okay, there's a lot of doors. Okay. So let's consider, let's see, maybe I'll skip that part. Okay. So let's consider the following problem. Let's suppose that we have a magnetized neutron star orbiting a black hole. And of course the black hole, the radius of the horizon is, if it's a spinning black hole, let's call it just the gravitational radius is 1.5 kilometers. M over M sun. I think Rain was using short shield radii, so he had 3 instead of 1.5. So that's GM over C squared rather than 2GM over C squared. So 7 solar mass black holes are getting to be roughly the same size as neutron stars. So here's the neutron star, and let's imagine that the neutron star is magnetized. So it has, let's say, a dipole field. Okay, so there's some field lines which are coupling the neutron star to the horizon of the black hole. And the black hole is orbiting, and typically the black hole's orbital velocity will be different than the rotational velocity of the neutron star. And maybe typically the neutron star is actually slowly rotating because tides don't have time to lock the neutron star. And so if it's a slowly rotating neutron star, basically the black hole is moving through the magnetosphere of the neutron star. Okay, so if we pretended that the black hole was a good conductor, and we'll get to what its actual resistivity is, if we pretended that that was true, then the voltage V that I would develop across these field lines, if this was a good conductor, would just be the integral of the electric field ds across the field lines. And the electric field that I see in the rest frame of the black hole will just be V cross minus V over C cross B in Gaussian CGS units. So this is minus the integral of V over C cross B ds. And the velocity is just the orbital angular velocity times r, maybe minus the rotational velocity of the neutron star. So that's the angular velocity, the Keplerian angular velocity, let's call that omega k, minus omega of the neutron star, which maybe typically is like 0, divided by c, so that's the V over c. Then we need B of r, so if this distance is r, right, this magnetic field of the dipole is going to be much smaller than that at the surface of the neutron star by 1 over r cubed, and then there'll be, twice the radius of the horizon with this length. And implicitly in writing this down, I'm assuming that the picture is the way I drew it, that the black hole is kind of small. The black hole horizon is small compared to r. It's not a supermassive black hole where the horizon is much bigger than this radius r. So this is sort of appropriate for black holes less than 10 or 20 solar masses, but not for very massive ones. But it would be easy to switch this if we wanted to do the more massive case. Okay. So, as I said, let's assume the neutron star is spinning slowly. Then this omega k is just square root of gm total over r cubed. And let's suppose the black hole dominates, so the m total is roughly the mass of the black hole. So it'll look like gm over r cubed. And this b is just the surface magnetic field of the neutron star times r neutron star over r cubed, the radial dependence for a dipole field. So collecting everything, we get V, the voltage is r over c, square root of g mh over r cubed, d0 r neutron star cubed over r cubed times gm over c squared, and I've dropped the 2s and 4s that might be floating around. Okay, so that's the voltage. So in order to get the power dissipated, we need the resistance in the circuit. V equals IR, so we get the current, we need the resistance. So the current we get from the voltage is equal to the current times the impedance of the black hole plus the impedance or resistivity of the magnetosphere. And I can do it later if you want, but the black hole basically acts like a really good vacuum, so the effective resistivity of the black hole is that of free space. It's just like an antenna, right? If you have an antenna in a circuit and you put an oscillating field through the antenna radiates, that radiates power that gets lost from your circuit, so it acts just like there was a resistor in the circuit. And the resistance of an antenna is 2 pi thirds times 4 pi over c, and 4 pi over c in engineers units is 377 ohms. 4 pi over c is 377 ohms. So the resistance of an antenna is 800 ohms times the wavelength, times the antenna size divided by the wavelength squared. So if you stick an antenna of your circuit, 377 ohms times L over lambda squared. Okay, so the black hole acts basically just like a free space antenna. So this is 377 ohms. I said is 4 pi over c in Gaussian units. In the magnetosphere, well, the magnetosphere is complicated plasma physics, so we call up Lorenzo Cironi or Anatoly Spitkovsky or something and ask what's the resistivity of the magnetosphere, and hopefully they'll say there's an answer also of order 377 ohms, because that maximizes the power. So let's optimistically assume that they say it's 377 ohms. If they say any other number, it's going to be worse. It'll be less power. But best case is they say 377 ohms. So then the power is, so the power dissipated. So the power dissipated in the black hole we don't care about. That just goes into the black hole. We care about the power dissipated in the magnetosphere. So the power dissipated in the magnetosphere, P magnetosphere, is I times the voltage drop across the magnetosphere. So we have a little circuit, we have our voltage V, and then we have the magnetosphere, and we have the black hole. And the resistivity of the resistance in the black hole is 377 ohms. The magnetosphere is some Z, which optimistically we would get the same as that. So this is the current times the resistance in the magnetosphere. And the total current is given by this equation, so it's just I is V divided by the sum of the resistances. So this is just, in terms of V, this will be V squared over ZH plus Z magnetosphere squared times Z magnetosphere. Okay, so this is just the I is V over the sum squared and then times the magnetosphere. Okay, so if you look at this equation, you see if the magnetosphere has zero resistance, this is zero. If it has infinite resistance, this is zero. And if ZH equals Z mag, then this is the maximum possible value. So best is when you impedance match, so the magnetosphere matches the black hole. So Raim is looking anxious, so I'll just put the numbers in. So we had the voltage that we calculated over here. Okay, we square that, plug into here, take 377 ohms for the magnetosphere. That will give the maximum power, and we can now calculate the maximum power. So I'll skip the algebra and write down this maximum possible power that we could extract in the magnetosphere. And that's basically C over 16 pi R neutron star to the 6 over R black hole to the 4th, B0 squared, R horizon over R to the 7th. And with numbers, that's 6 by 10 to the 44 ergs per second, B12 squared, R neutron star over R black hole, 4th. Okay, and the last equation I'll write down is if we integrate this over the gravitational wave lifetime. In other words, we consider this thing radiating that luminosity as it spirals in through gravitational radiation, we get the total energy that's radiated, right? This is power in ergs per second, but the neutron star lifetime, only the last orbit lasts for a millisecond, so it's like 1,000th of this. So we'd like to know the total energy. So the total radiated energy, again, the maximum possible, assuming the magnetosphere is impedance matched to the black hole, is the integral of this magnetosphere max dt. And you can write this as dt dr and use the in-spiral formula to get the total energy. And that is where things get depressing. 5 by 10 to the 38, B12 squared ergs, R neutron star over R the N. So clearly this depends on how close you get cubed. And then there's M over M neutron star.
All of which is produced at the very last moment.
Yeah, basically all of this is in the last instant. So if you remember, the radioactive decays were producing 10 to the 47 ergs. So to get even competitive with that, we really need magnetars like 10 to the 16 Gauss. Okay. So my guess is that, again, despite great enthusiasm, maybe this is a way to make fast radio bursts, not the repeating ones, but the one-off ones, maybe. But to get anything interesting, sadly, remember a fast radio burst in the radio alone is 10 to the 41 ergs, isotropically. This is entertaining. There are many papers of this sort, some by Jan Levin and Norm Murray and others proposing this, but I think unless we have a lot of extreme magnetars, I'm going to vote for the boring accretion and radioactive decay as the dominant sources. I just thought I'd work through.
Thank you very much.